Hello. Today, we want to talk about calculus in polar coordinates. So last time we talked about polar coordinates and this sort of idea that breaking the plane into concentric circles and these kind of rays from the 0, 0 was another way to describe every single point in the plane. So you can sort of give me a radius and an angle from the x-axis, and that will determine exactly one point on your curve. Okay, so now the idea here is great because now we can do things with functions that were not functions before. So things like a circle are very easy to describe. Things like a what we call a rose. So there's actually petals along this thing, and so that's a rose. That's going to be really easy to describe. It's just a function of theta. So this is great. So now what we want to do next is we want to say that's awesome. Now what we're going to do is talk about doing calculus in this format. So to look at the slope of the line tangent to the curve, what we're really looking for is, again, a change in y over a change in x. And so to find the change in y over change in x, what I do is I use this transition that we had talked about last time from r theta to xy. And then we want to use that to like find dy dx is essentially what we're looking for. So you can see that x is r cosine theta and y is r sine theta. So this was what we did last time, saying, all right, so from our trigonometry, if you look at your triangle here, the r is here, the theta is here. To find the x and the y coordinate of this, you just get r cosine theta, r sine theta. All right, so that's our way of finding these things. That's awesome. Now what I want to do is I want to say, well, but r is also some function in terms of theta. So r is f of theta. So that goes in for each of the two r's here. And then I differentiate y with respect to theta, differentiate x with respect to theta, and then divide them. Now to differentiate y with respect to theta, I need to do a product rule on f of theta sine theta. So do the product rule, what I get is f prime of theta sine theta plus f of theta cosine theta. So the derivative of f is just f prime, leave the sine alone. Derivative of sine is cosine, and then leave f alone. All right, same thing on the bottom. I do a product rule of the x here. It's just going to be f prime of theta cosine theta minus f of theta sine of theta. All right, and so if this was me, and in particular, one thing to sort of note here, the minus here comes from the derivative of cosine. Derivative of cosine is negative sine. So that's where that minus comes from. So if this was me, what I would probably need to do is I would always remember this transition here with the f of theta kind of plugging into each of those r's. Mostly because I know I don't trust myself to sort of write this down correctly every time. I'm gonna screw something up in this formula, and especially if I try to memorize it, it's going to be really just awful. So instead, what I do is I memorize the fact that x is r cosine theta, y is r sine theta, r is f of theta, and then I do this dy d theta dx d theta, and then I differentiate top and bottom and go from there. And I could do the product rule each time. Sort of remembering that from Calc 1, that's fine. It makes it a little easier for me to remember the actual formula here. Okay, so let's sort of do an example here. So I've got the curve 5 sine theta. I'm trying to find the slope of that curve at -5/2 and 7 pi over 6. That's the place where I want to find it. All right, so what am I going to do? I'm going to do my x and my y. So my x is r cosine theta. So I get 5 sine theta times cosine theta. And then the y is r sine theta. So I get 5 sine theta times another sine theta. Okay, so the top here, the y is just 5 sine squared theta d, then that's going to be it, right? So now differentiating, I should get dy over dx. So the derivative of y, derivative of 5 sine squared theta, I get 2 times 5 sine of theta. Derivative of sine of theta is cosine of theta. So this is nice. The nice way, a nice reason to do this. I don't have to do a product rule on the top. Product rule on the top is gone because I have a sine times a sine, so it's just sine squared. I can do a chain rule here instead. The denominator, I do have to do a product rule because it's just 5 sine times cosine. So I derivative of sine is cosine. And then the derivative of cosine is negative sine. So I get minus 5 sine squared theta. So I sort of look at this, I get 5s are going to come out of this one, and I get 2 sine theta cosine theta. And then the bottom is just 5, and then cosine squared theta minus sine squared theta. All right, now I have to go back to trigonometry a little bit. I could plug in, and that's fine. I can plug in my 7 pi over 6, and that's great. It's a little tricky though, because 7 pi over 6 is not one of the nicer angles. It's not like it's going to be 1 or like root 2 over 2 even. It's going to be a little worse than that. So instead of trying to figure out what exactly I needed to get here, I'm going to simplify things a little bit. So 2 sine theta cosine theta is the same as sine of 2 theta. Then cosine squared theta minus sine squared theta is actually the same as cosine of 2 theta. So the 5s cancel, and I'm left with sine of 2 theta over cosine of 2 theta. So I get sine of 2 theta over cosine of 2 theta. And now from there, now I plug in my 7 pi over 6. In particular, I could even just do this as tangent of 2 times 7 pi over 6, which is the same as tangent of 7 pi over 3. And then I can kind of go from there. This is just going to be the square root of 3. Okay. So what we end up getting here is a pretty nice thing. It ends up being sort of sine of 2 theta over cosine of 2 theta, and I can run from there. I could also just plug things through. I get a bunch of 1/2s and root 3s over 2s and sort of cancel what I can. And hey, lo and behold, what I get is just this root 3. Okay. Okay, cool. So that's the slope of the line tangent to the curve. And then I can find the equation of the line tangent to the curve as well. So that's great. So and I can do anything I wanted to do with all that. So there's sort of all these sorts of different things now that I can do from Calc 1 using the fact that I know the derivative of this function at a point. Okay, so now we want to find the points where the polar curve has horizontal or vertical tangent lines. So what I'm looking for here is where is the derivative equal to 0, or where is the derivative undefined? So the denominator is equal to 0, but the numerator is not. Okay, so now I'm going to look at this one. I'm going to say, okay, so I need dy dx. Again, y is r sine theta, and x is r cosine theta. And r is 2 sine theta, so I end up with y is 2 sine squared theta. X is 2 sine theta cosine theta. I do the derivative again. This time I get 2 times 2 sine theta cosine theta divided by the derivative of the first, or I'll actually do the derivative of the second here. First, sorry, here is going to be 2 cosine squared theta minus 2 sine squared theta. The 2 is going to cancel here. This top is again, sine of 2 theta. And the bottom is just going to be cosine of 2 theta. So the question here is, this is tangent of 2 theta. Where is tangent equal to 0? And where is tangent undefined? Where tangent is undefined is where sort of the asymptotes occur, those vertical asymptotes and tangent occur. And where it's equal to 0, we're going to sort of have the sine equal to 0 in my angle. All right. So what I get here is that 2 theta is either 0 or pi or 2 pi or 3 pi and so on. 4 pi, 5 pi, 6 pi, so on. Right. Okay, good. And then what about the other side of it? So now on the other side of it, 2 theta is either pi over 2 or it's 3 pi over 2, or it's 5 pi over 2, or it's 7 pi over 2, or it is 9 pi over 2, or so on. So all the odd numbers over 2 are going to be pi over 2 are going to have where tangent is undefined. Okay, so now I divide both sides of this by 2. So it has a 0 slope or horizontal tangent when theta is 0 divided by 2 is 0. Pi divided by 2 is pi over 2. 2 pi over 2 is pi. 3 pi over 2 is 3 pi over 2. 4 pi over 2 is 2 pi, and so on. And then it has undefined slope when theta is all of those divided by 2 as well. So pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, 9 pi over 4, and so on. And notice I kind of think about this and I say, well, actually, if I'm thinking about my plane, I only have to go from 0 to 2 pi. And so I can cross out all the ones after this and get 0, pi over 2, pi, 3 pi over 2. Cross out all the ones between 9 pi and on, 9 pi over 4 and on. And so I get 7 pi over 4, 5 pi over 4, 3 pi over 4, and pi. Okay. Those are my angles where I have 0 slope or vertical tangent line. So 0 slope are the horizontal tangent line, vertical tangent line are where they're undefined slope. And so that's where we're looking. Okay, cool. So now we think about integration. So to integrate one of these things, what we did before is we broke my curve above the x-axis into these like rectangular regions, and then I added up a bunch of rectangular regions and did this sort of Riemann sum stuff and said, oh, look at that, limit that thing as the number of rectangles goes to infinity. This gets smaller and smaller, and then you actually get the exact area underneath this curve. Well, here, I'm going to do the same sort of thing, except now I need to think about my curve. So my curve kind of goes along of these circular regions, right? So what I'm going to do is I'm going to break my curve into small regions. Each kind of as a pi piece, a wedged pi piece centered at the origin. The radius is determined by the actual curve f of theta. And so I can kind of keep going here. I do this. This would be what we would call maybe like a left-hand curve or something like that, right? Left-hand approximation. And so each of these does not have a straight line on the end here. I should be a little more careful there. That's an actual curved line. And so it's a piece of a circle. And the circle has a center 0, 0. Radiuses are determined by f of theta. Okay. So what we're going to do is we're going to say, okay, that's great. So we need to now add up all the areas of these regions. Oh, shoot, what's the area of one of these regions? So the question becomes, what is the area of a piece of pi? Okay. The radius is something, it's f of theta. The angle that we have is whatever this thing is. I'm going to call that delta theta, because it's a small little angle, and then it gets smaller and smaller. And so the delta theta goes to 0. This whole thing just kind of goes to the exact area underneath this curve. And so what's the area of that piece of pi? Well, so what we're going to do is we're going to use the area of a circle to find the area of that piece of pi. So the area of a circle is pi r squared. Oh, but r in our case is f of theta. And this is the area of the whole circle, centered at 0, 0, radius of r f of theta. And then I'm going to say, okay, so how much of the circle? So the sort of ratio of the circle. So what ratio of the circle am I taking? Well, I've got this delta theta. That's the angle that I'm looking at. And that delta theta is how much of the whole region. Well, the whole region has an angle of 0 to 2 pi. So if an entire circle to go all the way around would be 0 to 2 pi. So it has a total length of 2 pi. So the ratio of the length that I'm taking here, the ratio of the circle that I'm taking here is just delta theta over 2 pi. So this is the ratio of the whole circle. So to find the area of this region, I take that ratio and multiply by the area of the whole. And what I get is the area of that wedge. Okay, so the area of the wedge, or that pi piece, is just given by 1/2 f of theta squared delta theta. And I put this k down here because I'm doing this over a whole bunch of different regions, right? And so I've sort of got these small delta thetas, and I'm going to add them all up. Okay, and so now I add them all up. All right, so I find the sum, and I do this sort of like 1/2 f of theta k squared delta theta k, and I want to go, oh, k is 1 to n, and then I take the limit as n goes to infinity. And this is sort of a Riemann sum thing. And what do I get? Well, what I get out of all of this is the integral. And so I get the area between theta equals a and theta equals b of this function f of theta, which is the radius in terms of theta, is just the integral from a to b, 1/2 f of theta squared d theta. So the delta theta turned into this d theta. The 1/2 comes from this sort of this ratio thing that I did. And then the f of theta squared is the r squared. And then the pi canceled because there was like a 2 pi on the bottom and a pi on the top. Right? So the pi r squared and the 2 pi, and the pi's cancel. And then I'm left with this like ratio of delta theta over 2 and f of theta squared. Okay. Cool. So it turns out this is actually really nice. Now, the hardest part will be figuring out your limits of integration. So I want to find the area inside of this curve, which is 14 sine theta. You know, that's not an easy task, because I need to figure out, well, what is that region? So if I look at that region, I need to figure out what is that region. So let's look at it. And so I can do this polar plot to figure out what it looks like. And it's going to be r is the square root of, what was it, 14 sine theta. And just let me double check to make sure that was right. Yeah. So what does the graph of this thing look like? So look at that. It's actually like it's like a circle, but not quite. In fact, you kind of look at this thing and it's got like a kind of a flat bottom, essentially. I would maybe call it like a mochi. So it's a little bit like a mochi because it sits down flat, but it's got a curved circular top kind of thing. So it's almost like a circle, but not quite. It's got this sort of flat bottom on the bottom of it. Finding the area of this thing could be a bit of a task, right? So I mean, if I were to ask you to find the area of this thing, you might be able to do it, maybe split it in half possibly, and do like one curve for the top and figure out the area of that. And you, well, maybe could find another curve for the bottom and find the area of that, but that's a little bit more of an ask there. So what are we going to do? What we need to do is we need to figure out sort of where does this start and so how far does theta need to go to map out this entire region? Now, the trouble here is, so something on Wolfram Alpha or your calculator, you can sort of you can do a whole bunch of these. You can just keep it going and going and going. So here it has it from negative pi to pi. Down below here, it's from negative 10 pi to 10 pi. It appears that the entirety is there from negative pi to pi. Do I actually need all of those angles to figure this, to find the exact curve here? I think the answer is no. So I think about this. This is all in quadrants 1 and quadrant 2. So my guess is I only need 0 to pi. So to hit quadrant 1 and quadrant 2, all I need is 0 to pi. And in fact, look at that. I get the exact same curve from 0 to pi. I can maybe test myself and say, oh, maybe it's actually only pi over 2. Like maybe I've gone too far. And you can kind of graph this thing and look, and oh yeah, no, it needs to be farther. It needs to be all the way out to pi. And so that's where we end up going. Say, oh, okay, so I need to integrate now this curve from 0 to pi. And the thing I'm integrating is going to be 1/2 f of theta square root of 14 sine theta squared d theta. Okay. So now, taking this back, we're looking for this region inside the curve, square root of 14 sine theta. So I integrate 1/2 from 0 to pi, 1/2 square root of 14 sine of theta squared d theta. So I end up with just 0 to pi. I have 1/2 and I have 14 sine theta d theta. So I don't want to skip that step there. So 1/2 and 14 is 7. I can pull a 7 outside of this. Now I integrate, and the antiderivative of sine is negative cosine. So I get 7 times negative cosine theta evaluated between 0 and pi. So plugging in here, I get 7 times negative cosine of pi minus negative cosine of, so let me put the 7 out of that, of 0. I'll put the 7 out in front to make it a little bit easier. And so what I end up with here is just going to be cosine of pi is -1. So this is a positive 1. Cosine of 0 is 1. 7 times 2 is just 14. So the area inside of this curve, inside the region, is just 14. So it encloses an area of 14 in this case. Okay. So this is pretty cool. I can kind of get this out of there. Other things we can do with this, I can now integrate also between two curves. So if I have a sort of outside curve and an inside curve, outside curve being f of theta, inside curve being g of theta, to integrate between the two, I integrate the f of theta, that gives me the area in here, and then I integrate between the g of theta, and I subtract off the integral of the g of theta to be what's sort of left over in between the two. Okay, so let's do that. Let's take a look. So all I'm doing here basically is just saying I still have the 1/2. I have now, these are in parentheses, f of theta squared minus g of theta squared in respect to theta, a to b being sort of the 2 points that I care about where they're between them, right? The theta values. So let's do an example here. So I want an area outside of a circle, r equals 1, inside the cardioid, 1 plus cosine theta. I find it beneficial, again, to go and maybe look at this. So I have a circle r equals 1. And then I have r equals 1 minus cosine theta. And then this one I'm going to take away from 0 to 2 pi. So I'm going to have it go out there. So you can sort of see what this looks like. That's the circle, that's the cardioid. And I think I have it wrong. I actually should have maybe 1 plus cosine theta. Sorry, that's my fault. So this should be 1 plus cosine theta instead of 1 minus. Okay. And so you can see it's a cardioid, meaning it essentially is a heart shape to it. And we can kind of go from there. Now, outside of the circle and inside the cardioid, the circle lies here, and it's radius 1. The cardioid is the heart-shaped thing here. And now I want to find outside the circle, inside the cardioid. I'm looking between here and here. And so what I need to figure out is where these two intersect. So these two intersection points are important. I want to integrate from the bottom intersection point to the top intersection point. So what are these two intersection points? Well, I can solve. So I'm looking at 1 and I'm looking at 1 plus cosine theta. And so I'm essentially looking, where is cosine of theta equal to 0? Well, that's going to be pi over 2. Also 3 pi over 2, but I'm actually going to take it as negative pi over 2, so that I'm kind of going from negative pi over 2 to positive pi over 2, just to make my life a little easier. So that's my 2 points of intersection. Because I can't really integrate from sort of pi over 2 to 3 pi over 2. It's just not going to go that way. So I need it from negative pi over 2 to positive pi over 2. And then I'm going to take and say, okay, so the outside function is 1 plus cosine theta. The inside function is 1. Multiply that all by 1/2. Integrate with respect to theta. So I'll do that. So integrate from negative pi over 2 to pi over 2. 1/2, 1 plus cosine of theta quantity squared minus 1 squared. Now what? I take that 1 plus cosine theta and I FOIL it with itself. That's going to give me 1 plus 2 cosine theta plus cosine squared theta minus 1. And then the ones, so the ones cancel, and then I just integrate each of those 2 terms separately. That's fine. Pull the 1/2 through, it gives me just cosine theta and 1/2 cosine squared theta, d theta. Integrate cosine, I get sine. So I can integrate these 2 things separately. Integrate cosine gives me sine. Integrate cosine squared. Well, cosine squared is not so nice, except we know that cosine squared theta is the same as 1 plus cosine of 2 theta over 2. So this is one of my trigonometric identities, right? So I know that cosine squared is just 1 plus cosine of 2 theta over 2. And so that's fine. And then what? Well, so then I integrate the 1/2. That gives me theta over 2. Integrate cosine of 2 theta over 2 gives me sine of 2 theta over 4. So I get an extra 2 in the denominator there, because when I integrate this, I do a u substitution where u is 2 theta, du is 2d theta, and then I'm going to go from there, divide by 2 and kind of split it in, and extra 2 gets picked up in the denominator. So I get sine of 2 theta over 4. Plugging in negative pi over 2 and negative pi over 2, sine of pi over 2 is 1. 1/2 and pi over 2 is pi over 4. So pi over 2 over 4 is pi over 8. Okay. Then minus sine of negative pi over 2 is negative 1. So plus 1 is going to give me 2. So I get this 2 from there. And then 1/2 and pi over negative pi over 2, again, it's being subtracted, is going to be another plus pi over 8. So pi over 8 plus pi over 8 is 2 pi over 8 is pi over 4. So the area inside the cardioid outside the circle is just 2 plus pi over 4. Cool. So just to summarize what we need here, so to get the slope of the curve, I'm going to use the formulas from trig that I have for x and y. So x is r cosine theta, y is r sine theta. R is f of theta. Plug the f of theta in to each of the r's in the x and the y. Differentiate the y. Divide by differentiate the x. Do a product rule on each of those. It's going to end up giving me this formula here. F prime of theta sine of theta plus f of theta cosine of theta over f prime of theta cosine of theta minus f of theta sine of theta. Okay. So that's how it works out. All right. And that gives me the slope of the tangent line. And then last thing we need, finding the area inside the polar curve, we have to find A and B values. So that's kind of the tricky part of it usually, is finding these A and B values. You may have to switch the A and B values. So if I'm talking about like inside the circle, but outside the cardioid, inside the cardioid and inside the circle, then I've got a little bit more trouble there, because what happens is my circle is here, my cardioid looks like there, and it looks like that. I'm looking for this region here. Well, from negative pi over 2 to pi over 2, the circle is sort of the function I want to integrate. But from pi over 2 to 3 pi over 2, the cardioid is the thing that I actually need to integrate. I don't want to integrate the circle because that's outside of all of this. So I need to sort of split these into two regions, integrate along one region, integrate along the other region to find the actual value inside of each of these things. All right. Then for two curves, all I need to do, subtract one from the other, sort of outside function, inside function. And again, they might split or change values there. And so for one curve, it's maybe a little easier. I just have to figure out what's the A and the B. For two curves, it's a little harder. I need to find those A and the B because it's the intersection points potentially of these things. And then finding which is the outside and which is the inside is not 100% clear right off the bat. So you have to do a little bit of work to find the outside inside functions. Okay, so with that, I think I'm going to let you go and try this and see what you can do. Thank you.